Okay, the second video for 8.4 is covering absolute convergence and then a couple more convergence tests, namely the ratio test, which is one of the most useful and important convergence tests in all of this class. So we need to start with the definition of absolutely convergent. So a series um, sum of a sub n is called absolutely convergent if the series of absolute values is convergent. So in other words, this series might alternate or might have some negative terms in it. If we made anything that's negative in that series positive, summed up all of those terms, then we would have, and the series converges as this absolute value of terms, then we can call the original series absolutely convergent. So the details of this will be more clear when we do an example. A series which does not converge absolutely, in other words, when we make these terms positive, and it doesn't converge. However, if it converges when these terms are mixed plus or minus, positive and negative, then we call that series conditionally convergent. So that's if it's convergent but not absolutely convergent. Okay, so now we have three classifications. We have absolutely convergent, we have conditionally convergent, and we have divergent for series, now that we've introduced these definitions. Now, if we have a series that is not doesn't have any negative terms in it, well, then there's no need to talk about absolute convergence. I guess by default, you could say that such a series is absolutely convergent. There wouldn't even be a question of conditionally convergent if all the terms were positive. So, but since we're dealing with alternating series in this section, these are relevant terms now. So we're considering the alternating harmonic series, which we've already shown by the alternating series test to be convergent. Okay, but we know that if we take the absolute value of this alternating series, then we've got just the original harmonic series. We just have that -1 to the n plus 1 goes away in the absolute value bars. And we know that this is a divergent P series. That's one way to say it. And we also recognize it as the harmonic series. It is a famously divergent series. Now, we note that, as I did before already, that its alternating form converges. We use the alternating series test to show that in the previous video in these notes. And so what we can conclude is that in its absolute value form, this thing is not convergent. However, it does converge when we allow the negative terms to remain. So then we can conclude that this series converges conditionally. It's conditionally convergent. It does not converge absolutely, but it does converge, on its own with its negative terms. So that's one that falls sort of in that middle ground of conditionally convergent. Now, one thing we can say is that if a series is absolutely convergent, then it's convergent. So we'll always keep that in mind. If it's absolutely convergent, then it converges in every possible way whatsoever. It can converge with a plus or minus thrown in there. That's a weaker type of convergence to have plus or minuses in there or not. If something is absolutely convergent, then it is any kind of convergent. So that's our strongest form of convergence. That's really what that statement's telling us. So rather than have to do two-part tests all the time and know this much about series individually, we've got a very powerful tool, and that's the ratio test. The ratio test checks for absolute convergence. It'll check for convergence of even a non-alternating series. So if we have a positive series, we could use the ratio test on that as well. It works on anything, and that's why it's such a very powerful tool. It could be inconclusive, though. So when I say it works on anything, we can apply it to anything. It might get us an inconclusive result, though. So let me show what this, or introduce this test. You take the limit as n goes to infinity of the ratio of a sub n plus 1 and a sub n. These are the series terms. You do the next term over the previous term, or a term over a previous term. And you take the limit as n goes to infinity with the absolute value. And if that limit is equal to L and it's less than 1, then we can conclude that this series is absolutely convergent. So that's very useful. On the other hand, if the limit exists and it's greater than 1, or the limit is infinite, then we conclude that the series is divergent. So there's a cutoff in between, right? Less than 1 strictly, greater than 1 strictly. When we're equal to 1, That's our only sort of bad news case. The ratio test is inconclusive. And it's not the worst news. We've got other tests we can apply to series. So we'll try one of those if that ever happens to us, which it should, at least in a few cases in the problems. So our first example says determine whether the series converges absolutely, conditionally, or it diverges. So again, if it passes the ratio test, then right away we can say it's absolutely convergent. It's that quick, that handy, and that easy. Another thing to note about this is there are no negative terms. So if this thing converges, it automatically converges absolutely because those are positive terms. So a good indicator that the ratio test is going to be useful is if we have a mixed polynomial and exponential expression. So k is a variable on the floor, or k is a variable in the exponent, or n's a variable on the floor, or n's a variable in the exponent. That usually indicates that the ratio test is going to be the place to go first. And that's because we get nice cancellations through these exponential forms of k. Now, this would be hard for any of the other tests we've used so far, so you kind of cross your fingers and hope that the ratio test works. If not, then there's probably a very particular trick to use. And that's just for the problems in this class, in this book, for this chapter. Real world, things could be a lot messier and trickier. So a sub k is just the term itself. And then a sub k plus 1, be sure to write that down carefully. Everywhere there's a k, you put a k plus 1. So there was a k, it's k plus 1. There was a k, and it's k plus 1 as well. Okay, so we've also noted off to the side here that this series is the series of its absolute values as well, because all of these were positive on the left-hand side to begin with. Just an interesting thing to point out and write over here. So let's proceed with the ratio test. We've got a sub k and a sub k plus 1, and we take the limit as k goes to infinity of the latter term over the previous term. So that is this expression over this expression as we have it here. And we note what I mentioned before is that we have a good cancellation here in the exponents. We lose a factor of k from each of these 2/3. The bottom one disappears, and we just have 2/3 to the first power that remains in the numerator. And that's that 2/3 that's right here. K plus 1 over k, well, that's just what remains of the rest of these terms. And we could split that numerator to simplify things and rearrange terms a little bit inside the absolute value there. That's how we get this line here. K over k plus 1 over k, splitting the numerator, gives us 1 plus 1 over k. As k goes to infinity, 1 over k goes to 0. So this expression is just 1, or 1 plus 0. 2/3 times 1 is 2/3. And we note that 2/3 is less than 1. And by the ratio test, that's the first condition, if the limit of this ratio, absolute value of this ratio, is less than 1, then we have an absolutely convergent series. So that's exactly what we've got here. So the series converges absolutely by the ratio test. Note the completeness of this answer. We demonstrate that the limit of this limit of the absolute value of this ratio is less than 1, and then we conclude clearly that this is convergent by the ratio test, or absolutely convergent by the ratio test. So that's a well-formed full answer for written assessments in the class. Okay, let's see some more. Determine whether the series converges absolutely, conditionally, or it diverges. So we'll commonly see the full run of things. Which type of convergence, or does it diverge? Okay, those are essentially what we're asking each time. Now this one does alternate, so there is a chance that it doesn't converge absolutely, but it does converge conditionally. The first thing we should throw at this, though, it's got mixed polynomial n to the 10th with 10 to the n plus 1 with exponential. N's the base down here, and n's the exponent here. So we've got a mixed scenario. The ratio test is one of the best for these things, for these types of series terms. So let's start with that. It's always probably your go-to test in checking series for convergence. So we'll start with it. With the ratio test, we write down n plus 1. So everywhere there's an n in this expression, we put n plus 1. So n to the 10th becomes n plus 1 to the 10th. And negative 10 to the n plus 1 becomes negative 10 to the n plus 1 plus 1. So that's n plus 2. So that's our a sub n plus 1 term right here. Now a sub n is the easier one. It's just a copy of this term all by itself, or just rewritten. So dividing each of these or forming their ratio with the absolute value. And now we just start to simplify things. Let's put these terms together, the polynomial terms over each other, and then we'll put the exponential terms over each other. And that's what happens in the next line. We have the following. Again, as before, n plus 1 cancels with n plus 1 factors here, and there's 1 left. So there's a negative 10 to the first power in the denominator. That's going to be this negative 1 over 10 here. And then off to the side, we've still got n plus 1 to the 10th over n to the 10th. Well, this is a to the 10th over b to the 10th. So we can rewrite it as a over b to the 10th. And that's exactly what's happened in this term. So we got n plus 1 over n to the 10th. Limit as n goes to infinity of all of this with absolute value here. And as we inspect this one, we realize that this again is going to be 1 plus 1 over n to the 10th power. And that's just, this is running to 0. So this is going to 1 plus 0. So it's 1. 1 to the 10th is just 1. So we have 1 plus 0 times this 1/10 that was just sitting there as an extra factor. It's positive because the absolute value. And we end up with that limit of this absolute value of the ratio as being 1/10, and that's less than 1 strictly. So we can conclude by the ratio test that this series is absolutely convergent. So it's a nice test. It can handle some really messy looking stuff, but one of your biggest clues that you should use the ratio test, if you're not inclined to use it first thing, is that you've got a mixed polynomial term and a mixed exponential term. So n is on the floor in one case, in one part of the term, and n is in the exponent in another part of the term. That is one of the best indications that the ratio test is now appropriate or is going to be useful. So one last test and example is the root test. This is a little bit less common, quite a bit less common actually. It's just a very particular case. So if we have a, n as a root in our series term, then our n, or a sub n to an nth power is what I should actually say. If we have an nth power, I'll just go to the example right away. If there's an n in our exponent overall, and that's on the outside of everything, then this is pretty classically the root test. So this one is it's just a dead giveaway. Everything is taken to an nth power or some multiple of an nth power or n plus 1 or something like that. Then what we're going to want to do is use the root test to show that this thing is convergent. Now note that we could possibly use this on something like a geometric series, but it might be a little bit overkill because the geometric series still has its own convergence test. And moreover, the geometric series convergence test will tell you the sum and not just that it's convergent. So it's a little more appropriate to use geometric only on geometric. But what the root test does that's better than the geometric is we've got a rational function in here. We have a polynomial divided by a polynomial raised to a power of n. The geometric series cannot handle that. What's in here has to be all constants for the geometric series to work. That has to be our ratio r. It has to be some number 1/3, 5, some kind of constant, real number, not a function of n. So this is where the root test sort of shines, even though it is a sort of a niche test for just this type of series term. The conclusions are the same. If the limit of the nth root of the absolute value of our series terms is less than 1, then it converges absolutely. Our series converges absolutely. If it's greater than 1, it diverges. If it's equal to 1, then the test is inconclusive. So it's always keep an eye out for that equal to 1 case, to be careful with that. So we have series n equals 1 to infinity, negative 2n over n plus 1, all raised to 5 to the n. We're asked to determine absolute convergence, conditional convergence, or divergence of this series. So we'll just we'll state we're trying the root test right away. Limit as n goes to infinity of the nth root of this whole term, the absolute value of this whole term. So nth root of 5 of this thing raised to the 5n is, well, this is 1 over n, right? So I'll write those details off to the side. We need to see that a little bit better. That might help. remember this. First things first, this thing with the negative in there can just go away, right? We've got, it's to the 5n and then times 1 over n. That's this fractional power, this root or fractional power in the exponent, 1 over n, and that comes out to, well, with the negative here, or with the absolute value signs out here, the negative's gone. We can strike that out right away. It's always going to be positive. So we should have it written as 2 to the n over n plus 1 to the 5th. The n is out of the exponent. That's the key thing, the key fact that we need to keep an eye on and use for the root test. The fact that we get rid of the n in the exponent, and that makes this limit that we're trying to assess more doable. So that should be a positive there. Or we just haven't canceled it with the absolute value bars yet. So maybe we'll just wait on that and see it done in the next step. It's positive there. And more importantly, the root test has done its job. That nth root has gotten rid of the n in the exponent. That's the whole point of it. And what we're able to do is work from here and say, okay, what does this thing do as n goes to infinity? Well, a lot of us might remember that 2n over n plus 1 goes to 2 as n goes to infinity. If you weren't sure or didn't remember, you can use this trick, divide by the leading term of the numerator on top and bottom, numerator and denominator. It's 1 over n divided by 1 over n. So we're multiplying by a form of 1 here. We end up with 2 over 1 plus 1 over n. And we can see clearly as n goes to infinity that 1 over n goes to 0. So this is just 2 over 1 plus 0, as we have it written below here, all to the 5th power. So 2 to the 5th is 32. 32 is greater than 1. We have a number that's greater than 1 in our limit of the ratio. And this is our second case. The series is divergent. So the root test tells us that our series is divergent. And this is a well-formed answer. We've shown what happens when we took the limit of the ratio, or sorry, in this case, the root of our term, and we evaluated that limit. Then we declared or stated or showed that it is greater than 1, or if it was less than 1, we'd say that. If it was equal to 1, we'd use any of those cases to determine what our conclusion should be. And in this case, it's greater than 1, so it's divergent. So that's it for 8.4. Remember, we saw the alternating series, the introduction to that. We saw the alternating series test. We've seen conditional convergence versus absolute convergence. We saw the ratio test and the root test. The most important one is probably the ratio test. Now, what you note, one last thing I can say about this, is if a series fails the ratio test, then you might still use the alternating series test, because if it doesn't converge absolutely, it might still converge as an alternating series, and that's exactly what the alternating harmonic series does. It does not converge absolutely, but it does converge as a alternating series. So that's pretty much the workflow for 8.4. So good luck with that.